Forecasting is a systematic attempt to probe the future under conditions of uncertainty. For instance, the government has to make a number of 5-year plans encompassing all the activities of the nation. These include education, health, housing, transport, food, and industrial growth. All these are part of a fast-changing world where the future is fraught with uncertainties. Yet, planning has to be done in spite of these uncertainties in a number of areas like population growth, socio-economic environment, and demographic factors. Man-made calamities like wars and natural disasters like floods and droughts could totally upset planned outlays. Yet, when we plan for the future, we can learn a lot from the past. The existing trends, suitably interpreted to account for future changes, can serve as reliable estimates of the things to come. Almost every business executive makes a forecast of one thing or the other. Consider the case of a cement manufacturing company. The chairman is worried about the glut in the market. This has resulted in underutilization of the plant capacity and declining profits. He has to take decisions regarding expansion, modernization, labor layoffs, and in other strategic areas for making future financial commitments. On the basis of his past experience and an evaluation of the current environmental factors like government policies, economic and political climate, he can identify various plans of action and the corresponding future scenarios. Then, depending on his subjective preferences, he can choose the most desirable scenario and the corresponding plan of action. It is clear that accurate estimates of future demand and other relevant variables will result in more effective and reliable plans. Often, these estimates are obtained by projections of past behavior. There are a number of important variables like demand and sales, capacity utilization, inventory levels, manpower levels, annual profits. These are obtained as a time series, and the plot itself is used to choose the appropriate model for forecasting. An error in forecasting could lead to erroneous planning and financial losses. This could adversely affect the very survival of the organization. There are many methods of forecasting. Broadly speaking, they can be classified into subjective methods and methods based on statistical analysis. Subjective opinion forecasts are dependent on hunches and experiences of salesmen, experts, and others concerned. The major advantages of subjective opinion forecasts are that individual experience or expertise can be taken into account. They are easy to operate in practice. However, the major disadvantages of this method include their unsystematic character, their subjective bias, which is likely to influence the forecast, and their production of non-reproducible results. That means that different individuals or the same individual at different times is likely to produce different forecasts. On the other hand, statistical analysis of past demand is a more accurate method of obtaining the forecast, provided the system of chance causes which operated in the past continues to operate in the future as well. The past provides a useful basis for decisions on future actions. Yet, one must modify the predictions from past data if one knows for sure that certain events will or will not happen in the future. For instance, let us consider the demand for car tires. This demand is likely to be influenced by factors like production of cars, P, life of tires, L, condition of roads, R, average mileage, M, price of gasoline, G, government policy with regard to automobiles, GPA. Amongst all these, the most important variable is the production of cars. This is because all cars do need tires, and a direct relationship can be established between the two. Car production is an independent variable. An independent variable can either be set to a desired value or else can be observed but not controlled. The dependent variable is the demand for car tires. This is also called the response variable. A dependent or response variable is affected by the independent variable or variables. For simplicity, we may assume that the demand for car tires is affected only by the production of new cars. Thus, D is a function of P would represent a simplified model of tire demand in which there is only one independent variable, namely car production. The demand for car tires, which is the response variable in this case, could also be modeled as a function of the other variables already defined. For instance, a model of the type D, a function of P, L, R and M, represents a model with 4 independent variables, namely production of cars, life of tires, condition of roads and average mileage. Let us now consider the situation faced by a soft drink manufacturing company. This company has to plan its production and distribution on a daily basis for the peak summer season. Each day, the company vehicles go out to make more deliveries to retailers who order on the spot and take their requirements. If they carry less stock, they lose sales. If they carry more, there are returns, resulting in larger inventory costs. The company wants to have a fairly reasonable estimate of the sales so that the trucks carry adequate stock. Accordingly, a marketing consultant was engaged. He had in-depth discussions with the marketing staff and retailers to determine the variables that are related to sales. After analyzing the company records and discussing with the company's field force, the consultant made the following assumptions. The sales of cold drinks are directly related to the day temperatures. Hence, temperature is the most important variable affecting the sales. Over a short period of forecasting, the effects of other variables like competition, advertisements, general economic conditions, etc., would not be significant. In consultation with the marketing manager of the company, they decided to forecast sales on the basis of the day temperatures. The company had maintained records of day temperatures on a daily basis with corresponding sales. From experience, it was decided that a day temperature gap of 5 degrees centigrade would be relevant for forecasting purposes. Accordingly, sales figures at temperature intervals from 10 degrees centigrade to 45 degrees centigrade were tabulated. Temperatures below 10 degrees centigrade and above 45 degrees centigrade were considered to be rare and were therefore ignored from the exercise. Since there was only one variable, that is temperature, which affected sales, the marketing consultant decided to use simple regression analysis to estimate a linear relationship between the two variables of interest, that is, day temperature, X, and the number of crates sold, Y. The linear relationship between the two variables is mathematically represented as Y dash is equal to A plus BX, where Y dash represents the forecast of Y. Now, what is needed is a means of estimating the values of A and B. These are known as parameters in the equation of the straight line. Statistically, the formulae to determine the two parameters A and B are B is equal to N summation xy minus summation x into summation y divided by N summation of x square minus summation x whole square, and A is equal to summation y divided by N minus B summation x divided by N. These calculations can be easily performed by using a table. Here, x bar is equal to 220 divided by 8, which is equal to 27.5, and y bar is equal to 227 divided by 8, which is equal to 28.375, and b is equal to N summation of xy minus summation x summation y divided by N summation x square minus summation x whole square, which is equal to 8 into 7290 minus 220 into 227 divided by 8 into 7100 minus 220 into 220, which is equal to 58,320 minus 49,940 divided by 56,800 minus 48,400, which is equal to 8,380 divided by 8,400, which is equal to 0.997. Similarly, A is equal to summation y divided by N minus B summation x divided by N, which is equal to 227 divided by 8 minus 0.997 into 220 divided by 8, which is equal to 28.375 minus 27.417, which is equal to 0.958. After determining the values of A and B and putting them into the equation y dash is equal to A plus bx, we find the following relationship. Y dash is equal to 0.958 plus 0.997x. Now, the sales on a particular day can be estimated by putting the temperature of that particular day in the determined regression equation. Suppose the temperature for a particular day in June is estimated to be 45 degrees centigrade. Accordingly, the sales on that day are likely to be y dash is equal to 0.958 plus 0.997 into 45, which is equal to 45.828 in thousands of crates. Next, the marketing manager would like to determine the level of confidence of this forecast. For determining the level of confidence, the consultant applies the technique of the standard error of estimate. The formula for the standard error of estimate is SE is equal to square root of summation E square divided by n minus f, where E is the error in the estimated value as compared to the actual value of the variable, n is the number of observations, and f is the degrees of freedom lost, which is equal to the number of parameters estimated in the regression equation, equal to 2 in our example. For our example, summation of E square can be computed from this table. First, the forecast value is obtained from the regression equation y dash is equal to 0.958 plus 0.997 into x. Then, the errors in individual forecasts can be computed as y minus y dash. Next, the column of error squares is constructed. And finally, summation E square can be obtained by summing this column as shown. A comparison of predicted and actual values can be effectively shown on a graph. Hence, standard error of estimate SE is equal to square root of summation E square divided by n minus f, which is equal to square root of 94.84 divided by 6, which is equal to square root of 15.80, which is equal to 3.87. The standard error of estimate can be used to construct confidence limits on the forecast values as follows: plus minus 1 SE for 68.26% confidence, plus minus 2 SE for 95.46% confidence, plus minus 3 SE for 99.74% confidence. Thus, for the day when the temperature is likely to be 45 degrees centigrade, our forecast value of crates sold, determined as 45.823, represents the mean or expected demand. We can be 95% confident that the demand will lie in the interval 45.823 plus minus 2 into 3.87, or 45.823 plus minus 7.74, or in the range between 53.563 and 38.083. By using the method of regression analysis, the cold drinks company could forecast its daily sales with certain confidence levels and could accordingly plan its various activities. This is the flow chart used for applying regression analysis in practice. The first step is to plot or tabulate data. In the second step, we hypothesize the form of the function to be fitted. The third step involves estimation of parameters of the chosen function. The least squares method is commonly used for this. In the fourth step, a check of the adequacy of the model is made. If the model is adequate, then the model is used for planning purposes. In case it is not adequate, the model is revised and other functions are tried. If there is a large difference between the calculated and actual results, the model has to be revised. This revision could mean changing the form of the functional relationship, or it could mean the inclusion of new variables in the model. Regression analysis has many practical applications. For example, in a hospital, the authorities wish to study the incidence of heart attacks at different hours of the day. This analysis can help the authorities in planning the assignment of medical staff and assistants during peak and slack hours for effective medical care. This would help identify stress factors responsible for peaks in the occurrence of heart attacks and suggest suitable remedies. We now present some results of a case study conducted on cardiac patients reporting for treatment at a city hospital. The number of patients admitted over a month at different times of the day was recorded. A periodic function of the type ft is equal to a plus u cos 2 pi t by 24 plus v sin 2 pi t by 24 was fitted to the data. The plot obtained was ft is equal to 8.333 minus 3.0421 cos 2 pi t by 24 plus 1.322 t sin 2 pi t by 24. This is a graphical display of the function. The R-square value, which measures the efficiency or quality of the fit, was rather low at a value of 0.4412. To improve the quality of the fit, it was decided to try a second harmonic to model the data. The equation of the second harmonic is ft is equal to a plus u cos 2 pi t by 24 plus v sin 2 pi t by 24 plus p cos 4 pi t by 24 plus q sin 4 pi t by 24. Here a, u, v, p and q are parameters to be estimated from the data. When fitted to our data, the results were ft is equal to 8.3333 minus 3.0421 cos 2 pi t by 24 plus 1.3227 sin 2 pi t by 24 minus 1.3883 cos 4 pi t by 24 plus 0.3720 sin 4 pi t by 24. A graphical display reveals the double harmonic. The R-square value has now improved to a figure of 0.5240. It may be mentioned that a value of 1 for R indicates a perfect fit. A value of 0 indicates the worst possible fit. This is why the numerical value of R square may be treated as a measure of the efficiency or quality of fit. However, in other situations, there may be no simple relationship between the variables. The behavior of the response or dependent variable may be governed by a number of independent variables. In that case, the function will appear as y is equal to a function of x1, x2, x3, and so on up to xn, instead of the simple regression function y is equal to fx. Alpha is a company making reinforced concrete products for construction purposes. It was interested in accurate sales forecasts rather than relying on linear extensions of past growth rates. The three independent variables considered to influence the sales of Alpha were identified as population, construction employment, and the previous year's building permits. The historical data on Alpha's sales, the dependent variable y, and the three independent variables was collected. From this data, the correlation coefficients between all pairs of variables could be calculated. From this simple correlation matrix, we see that all the variables x1, x2, x3 show a high positive correlation with Alpha sales, the variable y. The model chosen for predicting Alpha sales was y is equal to b0 plus b1x1 plus b2x2 plus b3x3, where y is equal to Alpha's sales, x1 is equal to population, x2 is equal to construction employment, x3 is equal to building permits in previous year. b0, b1, b2 and b3 are the model parameters. For the 15-year historical data, the parameter values were b0 is equal to minus 208.69, b1 is equal to 22.91, b2 is equal to 157.69, b3 is equal to 155.78. The measures of goodness of fit were R value is equal to 0.9725, R square, or the percentage of variation explained, is equal to 0.9457. A comparison of the data and the forecast made by using this model for the last 15 years is graphically presented. To use this model for forecasting, the projected values for each of the three independent variables have to be obtained. Then, by using the functional relationship, the forecasts of Alpha's sales can be obtained for years 16 to 22 as shown. The 90% confidence intervals for the forecasts can be obtained in this manner. We have seen the applications of regression in actual case studies involving one or more independent variables. The success of regression in real life hinges on selection of the right model to suit the situation at hand.
one model cannot be applied in all situations. The right model has to be chosen from a variety of models that are available. The choice can be guided by the quality of fit as measured by the R-square value, the computational resources available, the degree of accuracy desired, and of course, the importance of the decision to be based